For any assignment-related queries, call us at +1 678 648 4277. You can mail us at support@computernetworkassignmenthelp.com, support@computernetworkassignmenthelp.com, or reach us at https://www.computernetworkassignmenthelp.com. Problem 8-1. A simple simplex example. Consider a linear program, LP, consist ing of two variables x1 and x2 satisfying the following three constraints. The goal is to maximize the value of the objective function p is equal to 4 times 1 plus x2. A. Draw a diagram of the feasible region. Solution. Figure 1. The feasible region of the LP problem. Image courtesy of finite mathematics and applied calculus. B. Write the given LP in standard form and transform this standard form representation into Slack form. Solution. Standard form, maximize p is equal to 4 times 1 plus x2, subject to. C. Use simplex to solve the resulting Slack form LP. Identify the pivots you choose and give the resulting modified LPs and the successive feasible solutions. Indicate the successive solutions on your diagram from part A. Solution. Start with x1 equals x2 equals 0, x3 equals 10, x4 equals 20, x5 equals 24, that is, the solution 0, 0, 10, 20, 24, with objective function value p equals 0. The first non-basic variable we select for pivoting can be either x1 or x2, since both have positive coefficients in the objective function. To be specific, let's choose x2. As we increase x2, the values of x3 and x5 decrease. The limiting constraint is the one for x5. We can only increase x2 to 8, because any more would make x5 negative. We exchange x2 with x5. We solve the third constraint for x2, obtaining x2 equals 8 minus 1 3x1 minus 1 3x5. Then we substitute, resulting in the following new LP. Maximize p equals 8 plus 11x1 minus 1x5, subject to. We get a new solution by setting the non-basic variables, x1 and x5 equal to 0 and calculating the others, 0, 8, 2, 28, 0. The value of the objective function is now p equals 8. The only option now for pivoting is x1, because the coefficient of x5 in the objective function is negative. As we increase x1, the values of x2, x3, and x4 all decrease. The limiting constraint is the one for x3. We can only increase x1 to 3. We exchange x1 with x3 and solve the first constraint for x1, obtaining x1 equals 3 minus 2 3x3 plus 2 1 x5. We get the following new LP. Maximize p equals 19 minus 11x3 plus 3x5, subject to. We get a new solution by setting x3 and x5 to 0, obtaining 3, 7, 0, 14, 0. The value of the objective function is now p equals 19. Next, we pivot on x5. Increasing x5 causes x4 and x2 to decrease, with the limiting constraint being the one for x4. We exchange x5 with x4 and obtain x5 equals 6 plus 13x3 minus 255x4. We obtain the following new LP. Maximize p equals 28 minus 85x3 minus 53x4. We Get a new solution by setting x3 and x4 to 0, obtaining 6, 4, 0, 0, 6, with an objective function value of 28. At this point, no further pivots are possible. Their coefficients in the objective function are both negative. Thus, an optimal solution is x1 equals 6, x2 equals 4. In the above process, we started from the basic solution 0, 0, meaning x1 equals 0, x2 equals 0, gradually improved our estimates through 0, 8, 3, 7, and finally arrived at the final solution, 6, 4. In Figure 1, this corresponds to traversing 4 corners of the white region starting from the origin in the clockwise direction. D. Give the dual LP of your standard form LP from part B, and give its optimal value. Hint: use your solution to part C. The solution: the standard form LP from part B is maximize P is equal to 4 times 1 plus x2, subject to. As in CLRS P880, the dual LP uses new variables y1, y2, and y3. The LP is minimize 10y1 plus 20y2 plus 24y3, subject to. By LP duality, Theorem 29.10, the minimum value for this LP is 28. This value is attained when y1 equals 5,8, y2 equals 5,3, and y3 equals 0. You can find this solution manually, or by considering the final slack form LP in your solution in part C, and using formula 29.91 on P882. Problem 8-2. NP completeness. In this problem, you will prove NP completeness of a few decision problems. To prove NFARDness, you may reduce from any problem that has been shown, in class or in CLRS, to be NP complete. A. Let triple SAT denote the following decision problem. Given a Boolean formula phi, decide whether phi has at least 3 distinct satisfying assignments. Prove that triple SAT is NP complete. Solution: to show that triple SAT is an NP, for any input formula phi, we need only guess 3 distinct assignments and verify that they satisfy phi. To show that triple SAT is NP hard, we reduce SAT to it. Let phi denote the input Boolean formula to a SAT problem and suppose that the set of variables in phi are x equals x1, xn. We construct a triple SAT problem with a Boolean formula phi slash over a new variable set x slash as follows. X slash equals x1, xn, y, z. Phi slash equals phi. Now we claim phi is satisfiable if phi slash has at least 3 satisfying assignments. If phi is satisfiable, then we can augment any particular assignment by adding any of the 4 possible pairs of values for y, z, to give at least 4 satisfying assignments overall. On the other hand, if phi is not satisfiable, then neither is phi slash. B. In problem set 1, we considered how one might locate donut shops at some of the vertices of a street network, modeled as an arbitrary undirected graph G equals VE. Each vertex U has a non-negative integer value P, U, which describes the potential profit obtainable from a shop located at U. 2 shops cannot be located at adjacent vertices. The problem was to design an algorithm that outputs a subset S U subset of or equal to V that maximizes the total profit U is an element of UP, U. No doubt, you found an algorithm with time complexity that was exponential in the graph parameters. Now we will see why. Define donut to be the following decision problem. Given an undirected graph G equals V, E, given a mapping P from vertices U is an element of V to non-negative integer profits P, U, and given a non